do the curve fitting. And next thing is how to use that. And the third thing is to solve a simple problem by using that. I will give you a very simple example today and show you how to use that. Cubic slant. There are different types of interpolation polynomials, as Newton, Gregory forward, backward, and Gauss forward, backward, and Stirling, and Bessel. And today we are going to focus on the cubic spline. That's the last one. Okay, here are some notation for the coefficient we use in the Newton Gauss backward-forward method, interpolation method.
A little lower on the side.
And as we know that the high-order polynomials are not always very good, and we have seen before, sometimes they tend to show large deviations from a smooth curve. And I will give you an example to show that even the linear spline curve fitting is better than higher order polynomials. A better method is usually to pass a set of cubics through points. Use a cubic in each interval, and the curve goes smoothly from each interval to the next according to the law of the beam flexure. There are different kinds of splines like linear, quadratic, and cubic. The most difficult one, or the most complex one, is the cubic. The relation for a cubic spline is given in here. That's for one interval. Practically, in draft technique, they use a spline to draw a smooth curve through a series of points, as you can see here, different points. At different interval, you use a spline to do the curve fitting. And notice that at the end point, the spline straight out. And the second derivative at the end point is 0. That is called a natural spline. Okay. Now we are going to derive a third order polynomial for each interval between the different nodes. As we know that if we have n data points, there will be n-1 intervals, and the 4 times n-1 unknowns coefficient to be evaluated. Why is that? As you can see here, because we have the B, C, D different intervals. There are a variety of end conditions. Two most popular ones are called the claimed and not a knock. What does that mean? We'll show you later. Because we want to derive the third order polynomial for each interval, we start with the I minus I plus 1 naught. This is the expression in that interval. And here, hi is the interval length. That means hi equal to x sub I plus 1 minus I sub I. Okay, this is the curve we are going to do the curve fitting, and we have one interval and two intervals till n-1 intervals, because we have n points. Okay, here's how we do the derivative of an interior node. Notice that this part is a little different from what is shown in the textbook, but ideally they are the same thing, okay? And you don't need to worry about that. We will post this to the website about how to do the derivative. We do the derivative by first take the first derivative and then the second derivative. The idea here is we want to represent D and B by using C and Ci or Ci plus 1. First, we do the first derivative of an interior node for this equation here. And we define that Bi plus 1 equal to this equation. Next thing is you do the second derivative about this expression, okay? The second derivative, and you get this. The equivalent of the second derivative at interior node is defined as the Ci plus 3 Dihi equal to Ci plus 1. And I suggested that after we post it to the website, you do the derivative by yourself so you will know how it really goes. And similarly, you can find the Bi plus 1 and Bi and Bi minus 1. This is the final expression we are going to use. You can obtain this equation by performing a little algebra and rearrange some terms. Finally, you can get this expression. This is implicit. As you can see that you have three anodes. They are Ci minus 1, Ci and Ci plus 1. How to solve that? You have to solve the system equation simultaneously. I'll give you an example after a while. And you rewrite the equation like this. Equation is valid for interior nodes I equal to 2 till n minus 2. Because as you notice that you have the subscript I minus 1, so you have to start from the second node, and you have the subscript I plus 1, so you have to end before the last node. And for a natural spline, the natural spline means the second derivative at the endpoint equal to 0. You can simplify the system equation like this. And we have different kind of AND conditions. One is called the natural condition, and the second one is the parabolic. Third one is not a knot, and the fourth one is clamped. As the first one, natural condition, you can see that the first and the last second derivative at the end point equal to 0. For the parabolic condition, you can see that the first point, the second derivative are equal to each other. The last one and the one next to the last one, the second derivative equal to 0. No, they are equal to each other.
What's the difference between these different end conditions? What's the goal of using either of them?
They will give you a different different fitting result. Okay, and generally the last two are the most popular used. So generally they can give you a satisfied result. And I will show you how to use them by using an example today. Like here, this is the comparison of by using the different AND conditions. And this is the natural condition, is this line, and the clamped condition, not a knot. And this is the initial curve is not shown here. Okay, in this slide, our purpose is to show you sometimes higher order polynomial interpolation not necessary to be better than the linear spline interpolation, as you can see here. For the original curve, we have sprung at the x equal to 0 location. Okay, there's a jump here. You use the 4-point polynomial interpolation, but you still can't approximate very closely to the original curve. And then you use the 6-point. But you induce some oscillation because of the settling jump at the x equal to 0 location. Even you increase the interpolation polynomial order and you keep increase the node number, but you still can't capture the feature very well, like here, because it is a straight line connection. As comparison, you use a linear spline, which is shown here. And as you can see, at each interval, you use the linear spline interpolation, and you get a much better result compared with even used higher order polynomial interpolation. Okay, this slide shows the spline fits of 4 points by using different kind of splines. Figure A shows the linear spline, and B is the quadratic spline, and C is the cubic spline. And as you can see, the interpolating cubic is also shown in the last figure. And you can do the polynomial interpolation by using MATLAB. There are already some built-in functions there. This is the simple example shows that how it can use the clamped on condition to solve the Runge's equation. This is the Runge's equation. It also had MATLAB also had the built-in function interp1 that's called the interp1 that provide a number of different type of piecewise 1D interpolation. And this can be nearest linear spline p-chips. Okay. This shows to do the curve fitting of the Runge's function. Runge's function is shown in the dashed line, and with the 9-point, total 9-point, not a knot spline fit generated by using MATLAB. And this is by fitting the Runge's function, use a 9-point clamped and spline fitting generated with the MATLAB. It's shown in the solid line here. Okay. This is the original curve we need to fit. Notice that the first derivative is 1. The first derivative at the endpoint here is 1. And the first derivative of the last point is -4. Okay. As we said that in MATLAB there are interp1 function, and they can perform different kind of piecewise polynomial interpolations. This shows you how it works by using different function options in the MATLAB. First one is linear, and it's called, second one called the nearest neighbor, third one called the spline, and the last one called the p-chips. Okay, here is an example, and I'm going to walk through example with you after we talk a little more about the last slides, and then we will go back. There are some other cubic relations, like Bessel. It has only a local effect if one of the points is changed. A cubic spline creates a global effect if the point is changed. And Bessel, some introduction about who is Bessel and what he's doing. He was a French engineer from the Renault Automobile Corporation in the 1960s, and he devised the scheme to design curves for fenders. And there are another kind of very popular spline. It's called the B-spline. This is another scheme somewhat similar to the Bezier curves, and the curve does not necessarily pass through all the data points. And the reason we introduced some other cubic relation is let you know there are still exist some other relations, not just cubic spline. But the purpose of today's class is let you know how to use cubic spline. Okay. Okay, I'll go back to the example problem and work together with you. This is the example problem. I'll copy it to the board.
Shalene went over cubic splines last time. I think probably everybody had